Example 3.3. In this example, we have two different flow fields with circular streamlines. The velocity profiles for each one is given, where V0 is the velocity at R equal R0. We need to determine the pressure distribution for each one of the cases, given the boundary condition that the pressure at R equal to 0 is equal to P0. To start the analysis, the first step is to write the equation that relates the forces, the mass, and the acceleration for the normal component. That is equal to minus gamma dz dn minus the derivative of pressure with respect to the n, and then this is equal to rho, and the normal acceleration, which is the tangential velocity, divided by r, where this is the radius of curvature. The first thing that we need to do is to be able to relate the normal component with the r variable, since the velocity is described in terms of r. From the graph of both of the cases, we could see that the direction of the radial coordinate system and the normal coordinate system, they are the opposite of each other. Therefore, we could say that n is the negative of r. Therefore, any derivative that we have with respect to n is going to be the negative of any derivative with respect to r. We also could see that the variable r is going to be equal to the radius of curvature. So we substitute into this equation. We also note that the elevation z does not change with the normal direction, so we are able to remove this term. And we substitute, because this is going to be negative and negative, they're going to cancel each other. Therefore, this becomes positive dp dr, and then we write this as rho v squared, and we replace the uppercase r with lowercase r. And now this is the equation that we're going to solve, that we're going to use for both of the problems. Let's start with case A. In this case, we have the velocity profile provided by this equation. Since we have to solve for the pressure distribution, the first step is to substitute this velocity into the equation and then do separation of variables so that we could find the pressure. So we do dp dr, and then we have rho divided by r, and then we're gonna substitute the velocity. The velocity is v0, r0, r, and notice that all of this goes to the second power. Therefore, we simplify it and we get rho over r, v0 squared, r0 squared, r squared. We cancel this r with 1 over here, and then we're left with simply dp dr is equal to rho v0 squared r0 squared times r. Notice that this equation is only a function of r, so we could switch the partial derivatives to total derivatives, and we could rewrite this equation as dp dr as rho v0 squared r0 squared times r. If we do separation of variables, once again we bring the dr to the other side so that each variable is in one of the sides of the equal sign. So we have dp stays on the left side, and then we have rho v0 squared r0 squared r dr. For this particular equation, we take the integral in both sides. The integral of dp is simply going to be p, and then we have rho v0 squared r0 squared r squared divided by 2 plus a constant. And we are going to use the initial boundary condition that indicates that our r equal to r0, the value of p is equal to p0. And we substitute it into this equation. So we said p0 is equal to rho V0 square, R0 square. We substitute R to be R0 square divided by 2, and C. Notice the R square and the R square cancel, and we could find that the value of C is simply P0 minus rho V0 square divided by 2. Therefore, the general distribution of the pressure is going to be rho V0 square, R0 square, R square divided by 2, plus the solution that we got for C, which is P0 minus rho V0 square divided by 2. Let's now do case B. We're going to follow basically the same procedure. We substitute the velocity into this equation. We have rho 1 over r, and then we substitute the equation, which is V0 R0 divided by r to the second power, and that gives us rho V0 square R0 square, and then if we multiply, this becomes r to the third in the bottom. Once again, there is only r in this function, so we could change this derivative to a total derivative, so it becomes the PDR rho V0 square R0 square divided by r to the third. We do separation of variables. The p stays in one side, and the other variables, the constant on the other variable r, goes to the other side. So to integrate, I'm just gonna put this as r to the -3, and then the r. I'm gonna do the integration in both sides, and then I get that p is equal to minus rho V0 square R0 square divided by 2r square plus a constant c. To be able to get the value of c, we apply the boundary condition that p is equal to p0 when r is equal to r0, and we substitute into this equation. Then we get p0 is equal to minus rho v0 square r0 square divided by 2r0 square plus c. Notice that the r squares cancel, and the value of c then becomes p0 plus rho v0 square divided by 2. We substitute into the original equation, therefore p becomes minus rho v0 square r0 square divided by 2r square plus p0 plus rho v0 square divided by 2. Please go back and be able to determine the pressure distribution for both cases. Notice that when we are looking for pressure distribution, we have to use separation of variables, integrate, and apply the boundary condition. If they were asking us simply for the pressure gradient, this would have been where you would have stopped. The pressure gradient for each one of the cases is simply the value of dPdr. However, if they're looking for pressure distribution, then you have to do separation of variables once again and substitute the boundary condition.